chairing the next session. Thanks, Andre. I'm looking for Christopher Wood. That's the man. Because he's going to be up next, and he is going to be talking on a study of, that's it, privacy and anonymity in the DNS. So, Christopher, you could come up. Thank you very much.
And can I just ask people that are, might have their backpacks or whatever on the chairs and make room for some other
Okay, cool. All right, good morning, or good afternoon, good midday-ish, everyone. My name is Chris Wood. I'm a fourth-year PhD student at UC Irvine, studying under Gene Sudik, focusing on computer and network security. In particular, I work on this project called Content Sector Networking. So this is a bit of a detour from my normal area of research, and an interesting one, so I felt compelled to come here and talk about it. So I'm going to be speaking about privacy and anonymity in the DNS. This is joint work, of course, with Gene and my former colleague Cesar Gali, who's now at Google, and this work was supported by VeriSign. So it's a pretty well-known fact that privacy is a difficult thing to achieve in the DNS. It first started out as a clear text protocol over UDP, where requests and responses were just sent, and anyone eavesdropping could just look at them. So encryption now is the default way that we try to protect these particular contents of the queries. So there's a lot of different ways, mechanisms to do this. The recent DNS OTLS spec or DNS curve from Bernstein. But as Shulman showed a couple years ago at WPES, side channels are kind of prevalent in the protocol. That is to say whether or not, or whether encryption is implied or not. You have information like timing, that is, the time it takes to resolve a particular query, the frequency of queries, response sizes that can leak information about the contents of them, and the resolution chains themselves, that is to say what stubs are actually addressed to resolve a particular query. So in our work, we're trying to focus on ways to plug these privacy holes, and so we look at a couple of different techniques, including like message padding, message interleaving, kind of in a mixed net fashion, artificial resolver delays, and chaffing, which is more kind of a privacy/anonymity technique. And I'll describe more of these in more detail as I get to them later in the talk. But I'm also going to be talking about an orthogonal problem that is client anonymity. For privacy, like I said, we're kind of focused on the content of the query itself, but we also wanted to address the question of whether or not queries can leak information about the origin. So by examining queries, can you figure out who has been sending them and potentially cause some kind of attack on their anonymity. And so that'll be the second portion of the talk. In the first one, I'm just going to focus on the privacy mitigation techniques. So go over our general approach, some of the techniques that we, or how we try to apply this particular approach, and then some results, and at the end finish up with the anonymity stuff. So there is a lot of material, but if you have questions, please feel free to come to the mic and raise them as I go. So privacy. Without actually describing any of the details first, I want to first lay out the adversarial model. So we have a simple DNS system where you have a client issuing a query to a recursive resolver, which will then talk to various stubs to resolve this to a particular address. And our adversary here is one that can snoop on the communication between client and resolver, or resolver and stubs, and can also query the resolver much like any other client can. And his goal, again, is to figure out what's inside the query. This is why encryption is kind of an appealing, or at least immediate thing we can apply, because it prevents trivial attacks by just snooping traffic on the wire and figuring out what's inside the query. But there's still those other side channels that we want to try to plug. So the first one is message padding, and we kind of tried to go at this in an ideal world. So Ideally, we would want our messages to fit within a single UDP packet, because then we could just pad to that maximum length, or TLS record rather, not just UDP packet. And then everything is fine. You're just always sending maximum size packets and just a single packet back and forth. But that's not always the case that a single request or response will fit within a single datagram. You might have to use multiple TLS records or multiple UDP packets to actually send the data to the destination. But we also wanted to make sure that the padding was not more than what's necessary, and that's difficult to kind of achieve because we don't necessarily know what the maximum necessary length is. So though there is an upper bound, theoretical upper bound, we don't want to always be padding to this maximum length, because that's an undue burden on everyone in between. So ideally we want to just get to the expected upper bound and not pad beyond that. And just a quick detour, so there are mechanisms to support padding in DNS. So for example, this eDNS or padding option, which allows the clients or servers to specify that padding is applied in a particular request or response message. But there's a note in this particular document that says that the usage of the padding is left unspecified. So that's kind of what we're trying to figure out, what is a good way to generate padding or apply it to queries or requests or responses such that it's actually useful. So a quick look at the queries, or a subset of queries, query names rather, selected from the Oarc data set. Shows that names themselves that are actually contained in requests and responses are relatively small, so under 45 bytes, that's not a big deal. And a lot of them kind of hover around the 10 byte range, which is pretty manageable, well within the standard MTU. But a chart from Schulman's paper a couple of years ago shows that in fact, the response size, for example, exceeds this standard 1500 byte MTU pretty easily for a lot of different types of records, and even peters off well beyond this upper bound of 5,000 bytes here. So it's not clear where the actual end is, and without knowing that, there's no kind of easy way to figure out what the ideal upper bound of padding should be in order to attain some kind of meaningful degree of privacy without just throwing a bunch of extra bits on every single packet for no apparent reason. There are a couple different ways to do it, and the way we kind of tried to approach it, like again, ideally we want the padding to be uniform across all the packets, but that's hard given the circumstances that we don't actually know what the maximum size is. So we take this trade-off approach where we break packets, I say responses here, but packets generally into what we call size tiers. So say, for example, if you have, your first tier might be packets that are in the byte range of 1 to 100 bytes. This is completely arbitrary, not to say you have a single byte packet. Second size would be the next 100 byte range and so on and so forth until you get to some imaginary upper bound X, and that would be anything, beyond that would be unpadded and just left as is. But the difficulty here is actually figuring out these boundaries and what's reasonable. Because if you have fewer boundaries, then you have to pad to the maximum length, which is, as I've been saying, enables more privacy but at the cost of significantly more overhead, which is what we don't necessarily want. But if we have more tiers, that means the range of possible padding options is much smaller, so we have less privacy, but less overhead. So there's the trade-off to be made here, obviously, and that's what we're trying to get at. And our approach is to build these kind of tiers dynamically based on the cumulative distribution of requests or packets. So for example, you might imagine a resolver or a stub server supplying responses with a size according to this particular distribution. You see there's a lot of responses in the 50 to about 230 byte range. There's not a lot of responses in the 50 to 230 byte range, but then there's a spike around 230 to 250, and then it kind of teeters off there afterwards. If you were to look at the kind of cumulative distribution of these requests, you could kind of bound them by the amount of area, or the area of requests under or in these particular ranges, and that then would become, for example, your tier boundaries for padding. So for example, anything that was within the 50 to 230 byte range would be padded to 230 bytes. If the response was in the 230 to 250 range, it'd be filed to 250, and so on and so forth. And here's another example of where we might have just less number of tiers, wider range of padding across the possible response sizes. So the approach is that you take, fixed number of tiers, and then based on, your observed cumulative distribution of requests, or responses rather, from resolver, you rebalance the boundaries as necessary going throughout. And there wasn't an easy way to kind of show the results of the padding other than just kind of showing in this kind of visual bounding box here. So we've implemented it in an open source Python version of the DNS resolver. So if you're interested in playing around with it and getting some data yourself, please contact me. I can provide that for you. So moving on to the next privacy technique we're focusing on message interleaving. And the goal here is to try to hide a couple different things, such as to say the frequency with which requests are made, the resolution time for a particular request, and the resolution chains that a particular resolution or request flow would follow. So you can kind of think of this as turning your resolver into a mixnet in a way, or a mixnet node. So to interleave messages, we necessarily need to batch them, because if you don't batch, you just are processing them as they come in, and request comes in, it goes out to the next stub you need to talk to, and so on and so forth. But by batching them, you're necessarily introducing a delay that affects the clients who are ultimately trying to get an answer to their query. So we want to minimize the query delays, by not making the system completely unusable, but while maximizing the amount of interleaving. And so the approach we took was to have the resolver kind of measure the average round trip time for a particular query to any of its subservers. We call this RTT prime, and then batch packets to be sent in windows of size RTT. So every single RTT kind of time epoch, the packets that have been batched up will be then be shuffled in some or permuted into kind of random order, and then issued in sequence, and then a repeat going on or going forward. So to visualize this pictorially, assume we have some kind of resolver sitting in the middle, be servicing 3 clients who issue 3 queries, which are batched up in sequence just as they arrive. You would apply some kind of shuffling algorithm at the RTT epoch boundary, and you would get a new order. Query 1 now is first, query 3, and then query 2, and you would just issue them in sequence, and then batch up the responses and then send them back to the resolver or to the client as needed. And so you just kind of work in this time-boxed bounding mechanism, or you work with this time-boxed bounding mechanism to control the flow of messages into and out of the resolver. And the results are really hard to read, so I'll just try to describe it in words. So what we did was take a particular PCAP file that had a lot of DNS traces in it, and just measured what the resolution time was for the client for this particular request, and then overlaid this RTT kind of scheduling mechanism onto the queries, and using the same RTT values, plotted what would have been RTT in the presence of the batching mechanism. And so it just looks like a lot of noise, but the trend is actually pretty similar, pretty constant for both, which leads us to believe that this batching effect pretty much has no real impact on the average resolution time, and therefore no effect on the perceived frequency of requests. Because if it did have an impact on the frequency, then the resolution time would have been appropriately affected as well. So in general, this is not really a useful technique for kind of plugging privacy, because the intuition is that in order to make it usable, you want the batch time to be very small, so within a single round trip time or some constant factor of RTTs. But DNS isn't a lot of queries aren't issued in that particular time window, so you're pretty much just sending out requests as they come in, because the RTT is really small. So Of course, you could increase the RTT window and batch more and more, but again, then you're just making the usability of the system significantly worse. So we opted not to do that. Okay, moving on. So the next one is this idea of artificial resolver delays. So timing side channels are a real problem in DNS and any kind of system with caching. Pretty much caching is known to be a very abusive side channel in many different ecosystems. So the idea here is to, instead of always just replying with the cache value right away to optimize latency for the client, to introduce instead an artificial delay that masks or mimics the original query that would have been sent out, and then replies with the response after that delayed time. So the approach, pretty simply, if a request comes into a resolver and the data is not cached, then resolve it and record the RTT. And for future requests, if it is cached, wait for that particular RTT time and then return the response. And so to test this, we took a number of pcat trace files, here's one of them, and extracted the queries that were contained inside them, repeated introduced duplicate queries or duplicate requests to actually make use of the caches, and then measured the average runtime time for every single particular domain. So in the caching case, or in this particular case without an artificial delay, the first one would induce a full resolution to resolve the query, and the subsequent ones for that same particular name would be served by the cache, and so the average time would go down. That's the blue line at the bottom. Excuse me, at the bottom. And with the artificial delay, the RTT time, or the service time, always stays at what the expected RTT is. So this is good. It's a simple process to do this, or a simple mechanism to implement in resolvers, and it kind of masks the presence of any upstream cache or any upstream recursive authoritative name server. So we found this to be a positive approach. But there's a couple questions that might be raised. For one thing, if it takes a very long time to resolve a query, you're punishing every single other client that happens to hit that cache value by making them wait for this same amount of time. I just used 0.1 second here as kind of an example. If that whatever that time is, if that is problematic and introduces a usability problem, then maybe this needs to be reconsidered. Also, in the very first, or in the description I just gave, we were using per query RTTs. So, if two particular queries had completely different resolution times, subsequent queries for those same names would be delayed for different amounts of time. And that can reveal a lot of information about, for example, what the resolution strategy is for that particular name. So if we want to mask that, the approach then is to delay everything for this maximum resolution time, which could hurt clients even more. So there's this inherent trade-off between privacy and usability that should be considered, and not trying to advocate one way or the other, which is good. Just that's something to be considered if you're going to think about applying this particular delay mechanism. Okay, so now that I've covered privacy, I'll move on to anonymity. And just like before, I'll describe the adversary model that I'll start with. So we have here just multiple clients talking to a recursive resolver, and then some stub servers sitting on the right. And our adversary here, instead of being one that's snooping on all the traffic, is a stub server who's trying to answer the question, who generated this particular query? And I just draw him as a single stub, but he could potentially be multiple stubs in a very paranoid view of the world. And he could be using this information he collects across multiple queries to answer this single question. And I'm not trying to argue that this is a particular realistic adversary, or we should be worried about this particular adversary. It was an interesting problem that we wanted to, or an interesting avenue we wanted to explore, rather. So the attack, the goal of the attack is basically as follows. So as a stub server only receiving requests, and you have no information about where the original request came from because it's hidden behind the recursive resolver, your goal is to use all the information contained in the queries to link them to specific clients. And there's a lot of different features you can choose from or extract from these queries to accomplish this goal. For example, you could look at the length of the query, the query target name, the actual value, the frequency, window frequency within which queries are issued, differences between components of related queries, the entropy of a query, and so on and so forth. And you can just hypothesize a bunch of different things that may or may not be useful. And there's other things that we potentially discussed, for example, using the knowledge of the resolution chain, but in the single or the stub kind of adversary approach, he doesn't have access to necessarily the entire resolution chain, so we just omit that particular feature. So our approach was pretty much as follows. For data, we asked a small set of users to run some evil script on their computer to capture DNS packet traces over the course of a day and repeat this, over a week or so, over the time frame of a week or so. And then this PCAP file would be split. This set of PCAP files would be split into training data and test data. And then the computation is pretty straightforward. We have a set of classifiers that we looked at, and for each combination of the feature sets that we were interested in, train the classifier and then run it to see if it can actually accurately detect or identify the origin of a query based on the feature set it extracted. And for classifiers, we use a number of ones like support vector machines, logistic regression, SUT, and decision tree. Those are not necessarily important. I'm not a machine learning guy by any stretch of the word. I just use the library to do this. So some of these might be better suited to this particular task than others. So I do not know which one is best. So that's why we just kind of shotgun and tried them all. And here's just a subset of the results. So the classifiers are on the left. The features we examined are in the middle. And the error rate for the classifier is on the right. And generally, this is indicative of all the results. So, having a approximately 50% chance of identifying correctly the right user is not very good. From a cryptographic perspective, having an advantage that's non-negatively greater than 1/2 is considered to be bad, but in this particular case, because the algorithms are, the classifiers are probabilistic, or the data is kind of random, the algorithm is going to be probabilistic, that we kind of deem this, or at least the features that we were considering ineffective or not useful in conducting this particular type of attack, and that's a positive outcome, I would say. There are certainly other features that we didn't look at that might be leveraged, but for these ones that we did examine, they're not the most useful. Assuming in some kind of crazy world where they are useful, we wanted to also see if we can make the anonymity problem a bit harder, and a standard approach to do that is to chaff, or to introduce a lot of chaffing traffic. And for this, we had a couple of requirements. First of all, we wanted the chaffing to be similar to existing queries, so it's really easy if you're constantly querying or asking for Facebook or Google or YouTube, and then you have some obscure domain name that's generated randomly, for example. That's kind of an obvious outlier, so we wanted it to blend in, and the rate at which the chaff is generated should also be legitimate, or resemble legitimate traffic. So the way we did this was, again, using these PCAP traces, we built a weighted directed graph of domain relationships, which I'll describe in the next slide. And then from that graph, basically conduct a random walk over it at a rate that's approximately equal to legitimate traffic and issue queries from it. So a domain graph is basically as follows. The vertices are a set of domain names, and the edges are between one vertex U to V if the vertex or the name associated with V was queried after U from the same address. The weight of the edge is associated with the delta between the timestamps. So you have a much larger weight if they were close together, and a much smaller weight if they're farther apart. And we did it this way because it implies some kind of relationship between the two domains. You might be on YouTube or Twitter, and then you might navigate to Facebook or YouTube by clicking links or something like that. And this is just an example of some completely clustered mess of a domain graph. Could not figure out how to plot this in a better way, so don't try to read it. It's just the random walk across this thing would yield completely, maybe nonsense domains, but that's one we came up with. The approach is what I just said. So given this domain graph, perform a random traversal at the average query rate, and the results, realizing this morning that I forgot to label the axes. So the x-axis is the time, the y-axis is an index or an identifier for the particular domain that was queried. So on the top you have queries that are issued with .chaff traffic, and then at the bottom is that same graph kind of superimposed with the addition of chaff, attuned to an appropriate level. And ideally we would want this to look completely unrelated to the not chaff one. So you can increase the rate at which chaff is generated to make this even further, or even make this look up even more noise. Again, that's a trade-off we have to make. So wrapping up, looked at a couple different privacy enhancing mechanisms. The artificial delays seem to be the only kind of useful one, particularly because they're more intrusive, really easy to implement, and hides a very important side channel that is timing. Anonymity, in the case of the adversary that we considered, seems to be not a problem right now, at least. There are certainly cases where stronger adversaries might be viable and they'll have a much easier time. For example, if the resolver is the adversary, it's not hard to figure out who's sending the query. Just look at the source address. If you really want to live in a paranoid world, you can always introduce query chaffing based on the technique we described to kind of unify traffic patterns. But again, at a significant cost. So that is it. Are there any questions?
Hi, this is Shane Kerr from BII. I think this is really good research. First question is, are you planning on documenting a set of recommendations, perhaps submitting them to IETF DNS Op or something like that?
If people would think that's valuable, then yes. I mean, maybe Deprive might find some value in this. If they will, then yeah, I would be willing to do that, of course.
I mean, I know certainly during the discussion of the padding option, for example, we explicitly said we're not going to make recommendations because we don't know what good recommendations would be. So even having not necessarily operationally tested, but at least some theory of operation behind how to do padding and things like that seems quite useful.
Yeah, I agree. We certainly need to do more kind of operational testing with it, and we were limited in what resources we had available.
Sure.
In UCI, so.
Sure, and I'm going to, well, I guess I'll go to the back of the mic.
You can take whatever, okay. I was going to say, you can talk offline.
Yeah.
Okay.
Hey, Michael, John Christoph from DePaul University. I was taking some notes. I thought this was very interesting, although I only spent a few minutes on it, so you may not be that impressed with the limited time I had, and if you're not, that's my excuse anyways. One first comment, you kept referring to this, this term stub server. Maybe this is a term that other people are using now I'm not familiar with. I think maybe what you meant is authoritative servers.
Yeah.
So just to clarify that, so for other people in the room.
Yeah.
So there's a few things. At the beginning you talked about padding, and I want to ask you, is the padding just on the response?
So in the scheme that I was kind of outlining, based on the distribution of paddings, yes, it would be on the response. You could, for example, imagine a resolver who's also accumulating this information and issuing out padded requests the same way.
So my only concern then is, in that particular case, is immediately came to mind is amplification that you might generate because of that.
Of course, that could be abused to, for example, make everything really large. To gain to play.
A couple of things. I thought when you were going through some of the ways to make things sort of blend in, I thought part of the way we get some of that now is with caching. So if there's maybe some additional ideas for you, if there's ways to do improving caching, larger shared cache, or having caches share amongst each other, sorts of things that might be interesting stuff to look at as well. And maybe opportunistic querying, for example, if someone's querying for www something, maybe you should add in as chaff, well, let's also query for mail or some other stuff that maybe we've seen in the past and that sort of thing. And the delay thing does look appealing, but I imagine that's not going to be very practical. I don't think anyone's going to purposely want their stuff to go any slower, so that's just my feedback for you on that. So.
Yeah, I opt for security and privacy over usability, so the world is now
Malfeber, one thing, on the delaying is that, of course, there are stuff out there that just gets resolved slow, and you could then kind of have a attack that utilizes that.
Excuse me, Sean, could we kind of cut it at Alison? We're running really late at this point, so we're kind of running out of time.
Talk to you offline. Oh,
Okay.
Such generosity.
Yes, I mean, that in itself could be a possible attack vector to it, or?
yes, that's true.
And do you, I mean, on the research that you did from the resolvers, the authoritative, was it just kind of, was it different resolvers or just one set of sort that you used and tried that?
It was just one resolver, and yeah.
Okay.
Like I said, we need to do more large-scale operational testing on all these schemes. TBD.
Hi, so John Hedman, USC. So it's really nice to see a survey of all the privacy protecting techniques here, especially from an expert in that field. I found, so there's always a trade-off, right? Cost versus private, what level of privacy you get. And on some of your things, you had a pretty good list of that, like when you were looking at introducing chaff queries. I thought for the earlier work about delay and padding, I didn't see a clean trade-off of exactly what my cost is versus my privacy benefits. I'd encourage you to put in some kind of trade-off graph.
That is a very good thing.
The other question in this audience is, and what about our poor servers? Because if you're introducing delay on the reply side, that's memory on a server, and I didn't see any discussion of that, so that might be something to think about.
Yes, yeah, that's a good point. We did not factor that into our decision, perhaps because we don't own and operate a server, so. I know.
Okay, thank you very much, Chris. As is obvious, our next speaker is Shane Kerr, and we'll be a little late for lunch, but not too much.
All right. So thank you, everyone. Well, hopefully you're not too hungry, and hopefully we'll have a little bit of fun with this presentation. So my name is Shane Kerr. I work for the Beijing Internet Institute. This is not at all related to my work. This is just something that I happened to notice, and I thought it would be interesting to dig a little bit into this. So you see on this slide here, there's a what the, and then there's a little funny symbol up there. That's the, as far as I know, that's the Egyptian hieroglyph that represents the underworld. So what the hell? And basically, I noticed at one point, as you do, that VeriSign IDNs support the Egyptian hieroglyphs. And I thought, wow, that's quite cool. Of course, I want domain names with Egyptian hieroglyphs in them. So how do I go about doing this? So I do what anyone would do in this situation, is I just go to some popular registrar. And I went to VeriSign itself, and I thought, because they're the ones that are acting as the registry, but unfortunately they can't do that. So, okay, whatever, Egyptian hands in the air. I tried a few more registrars, and it didn't seem to work. So I actually went to the RIPE DNS Working Group. I said, hey guys, what's going on here? And Joao Damas, who's in the room here, suggested, well, don't try to paste hieroglyphs into browsers and dodgy web pages and things. Just use the Unicode version. So if you don't know, Unicode is this way we have of encoding Unicode into ASCII in DNS. So I tried it with a few registries, and it failed. Registrars rather, and it failed. Oh, I should correct that. But then someone said try to use Gandhi.net, and it worked. So Ra Ra Ra, that's the Unicode for Ra, the Egyptian sun god. Now, I don't know why it worked, I have to admit, because they have a list of supported scripts, and weirdly, Egyptian hieroglyphs was not on the list, even though they have Coptic Egyptian, but anyway. But it did seem to work. I tried to use, when you get a domain from Gandhi, they offer you the ability to host the domain on their own servers. That didn't seem to work, so I said, that's all right. Didn't really bother me. I'm a DNS guy over on my own stuff. So I set up the DNS. I used Bind9 and Bundy, which is the failed Bind10 project, the open source version. And you just use the Unicode version, as was suggested, to configure it. Unfortunately, I couldn't do in bailiwick name servers because VeriSign doesn't allow Egyptian hieroglyphic glue. I don't know why. Even as Unicode, so I think it'd be okay, but it doesn't seem to work. They didn't support the A and Quad A records. So I just used out of bailiwick name servers, which is quite normal, a little disappointing, but there you go. I also didn't use DNS signatures. It might work, but by this point I was feeling like I'd already wasted way too much time on this little project. If you're feeling bold, you can try DNSSEC. In principle, there's nothing about DNSSEC that should be any different, but as always, these things are coded up in databases and web pages and things like that. So once I have my domain working, great. All I could do was dig on it. So I decided, well, now you have to go to the next step, set up a web page. Now this case actually was a little bit easier. I just used Apache for this, standard web server, used the Unicode version to configure it. Now, unfortunately, it's not TLS secured, so you can't go to the HTTPS version of the web page. I'm cheap, and Let's Encrypt specifically doesn't support Unicode. I don't know what their motivation is for that, but there it is. To be honest, at this point, after all the trouble I had getting just the DNS to work, I'm not really convinced that any other certificate authority would have had a much better time at it. All right, I've got DNS working, got a web page set up, and actually need to be able to go to the web page and have it look pretty and stuff. I run Debian for my laptop, so it's not a big deal. I was easily able to install Egyptian fonts, which conveniently also installed Sumerian fonts and runes and things like that, if you want to do that. Now, unfortunately, browsers have a special technique to make this stuff not work. It's an anti-phishing technique. So in this case, what you don't want is someone to have a domain name that looks exactly to a human like another domain name. So people could send out a mail saying, please update your Apple password, and they actually put a strange L from some other character set and things like that. So they make it difficult to use IDN. There's specific rule sets about this. There's a Mozilla page about how Firefox does it. So you can paste in the Unicode version, and then it will get converted to the IDN or to the Unicode version when you see it on the web browser. But unfortunately, with Lynx, the text mode browser, you have to use the Unicode version. So that's a bit of a bummer. And I didn't test email or Jabber or any other type of thing. So I just went for the web stuff. So that's basically it. The website's up and working still. I guess it will be until a year's gone by. I'm not going to renew the registration because it works. That's it. So yeah, any questions?
Paul Hoffman, just a comment. If people actually care about the Unicode stuff, not with just the examples of Egyptian, come talk to me, because I actually own example.com, E with an accent over it. And I also got example.org because originally different browsers would treat .orgs differently than .com. I still have them around. So, your question about you don't know why Let's Encrypt won't do IDNs, they thought that it was a security risk because VeriSign had told them that. And they're getting over that, and hopefully within the next 3 months they'll accept IDN registrations.
Oh, that'd be great.
Yeah, so if anyone knows anyone on the Let's Encrypt technical board, please come talk to me. I've been beating on them for that for over a year, and we're getting there, but I'm not sure when. That's
cool, yeah. I can see the anti-phishing things. I'm not sure I can understand the rationale to not issue certificates, but anyway.
Yeah, that was actually what, this is Allison Menken, that's what I was going to comment on. That was kind of eye-opening that they were so not, but that's great that there's a procedure. And I just thought this really, really fun, and thank you, Shane.
Sure.
Hi, Bruce Roberts, Domain Tools. If you want to play around with some more of this, some really fun ccTLDs provide all sorts of really odd Unicode. I registered integralsign.tk, and there's other things like chesssymbols.tk. So there's a whole host of some of our favorite unsavory TLDs out there that really let you do wild things with this. You can't get quite as far as you've gotten with the Egyptian hieroglyphics, but it's still interesting. You can get to resolvable websites.
I'm a great fan of TK because, as I said before, I'm cheap, so.
Yeah, well, that's part of the problem.
Yeah.
So Roy Adams from ICANN. I've got I played with a few cute ones in the past. For instance, you have http://www, which is actually one single label where the :// is a Unicode representation of the real ://.
Nice.
So that's one. Another one is you can actually get the HTTPS log, the one that's normally green on the left-hand side, as a Unicode character. And people think that's safe. I have an email address used for a long time where I had on the left-hand side of the user representation of the email address, you know, the stuff between, how do you call that, quotes, where it says Roy space errands. I had log Roy space errands, and all of a sudden people thought it was safe to talk to me because obviously I'm using PGP. So there's a whole sphere of things you can do there. And yes, the fact that you can register Unicode characters, that you can register xn-dash and some top-level domains that are left unchecked is a problem. Cheers, and thank you for this.
Great, thank you.
Thank you. That's the end of this morning session. I have lunch info that's been handed to me. It's in the Oak room. Where's that? That way. The lunch boxes on the top shelf is for everybody, omnivores and vegetarians. The second shelf, that's what's written here. I'm not sure whether the second shelf is above or below the top shelf. I assume it's below. The second shelf is only for pre-ordered dietary allergies and intolerances. So if you're feeling any of those, the second shelf is for you. See you after lunch. Thanks a lot.
Nothing like a couple more